Hello everyone, welcome to part 2 of the Proca equation. In this video we will be finishing our solution to the Proca equation and we will derive the most general solution to the Proca equation. Let's begin. So if you remember from our last video, we obtained this solution to the Proca equation. Now this is just one of the solutions to the Proca equation, which is built off of those positive energy solutions. And we also derived this equation, which is a continuity equation. And we used this equation to find our first solution. It turns out that we can use this equation again to find out about some physical constraints on the possible solutions to the Proca equation. So let's actually begin. So first, let's just plug in our solution to the Proca equation. Oh, and by the way, this e to the rho, that's just some 4 vector, and then this is just a plane wave. So plugging that solution in, we get e rho partial of e to the minus I k mu x mu. This equals 0, which means that e rho minus I k mu e to the minus I k mu x mu equals 0. So this means that this part has to be equal to 0, since we can't raise e to the anything and get 0. So this means that minus I e rho, oh, by the way, this has to be a k rho. This has to be a k rho, because this is a partial row, so these indices have to match, they have to agree. So this is going to be a k rho. So you have minus I e rho, k rho equals 0. We can then just divide both sides by -1, and we're going to get e rho k rho equals 0. So let's just erase some of the work that we've just done to make some more space. Let's bring our solution up. So we've just found some relation between our vector and the momenta. So if we can recall, k is just the 4 momentum vector, which is made up of k0, k1, k2, and k3. And k0, the first entry, is related to the energy. It's related to the energy of the particle, or I suppose the field. Now, yeah, it's actually proportional to that energy. Let's do the proportional sign. And then these bottom 3 components are proportional to the actual momentum of our particles. So this relation just relates the vector part of our EM potential field with the momentum of the actual field, or the momentum of the particles that arise out of that field. We will understand that more when we get to second quantization. So we can just choose we can choose a solution where the wave is moving only in the z direction, only in the z momentum direction. So that corresponds to making k1 and k2 be equal to 0. So of course, this just corresponds to us having some wave that moves only in the z direction. So we can choose this to be the z direction, and the wave only propagates in that z direction, momentum wise. Of course, you still have the energy entry, but that isn't related to the direction of the wave. So if we only have some wave moving in the z direction, this means that, so we can just expand this out. That's just E naught K naught minus EI KI, where EI KI is just some summation. And if we only consider a wave moving purely in the z direction, this just reduces down to E naught K naught minus E3 K3 equals 0. And since E naught K naught minus E3 K3 equals 0, this of course implies that E naught K naught equals E3 K3. You can then just divide both sides by K. We have E naught equals E3 K3 over K naught. So this relates our E3 component with the E naught component. And this is actually a pretty nice relation that we've just found out. Since recall that E has 4 components: E naught, E1, E2, and E3. And if we are considering a wave traveling in the z direction, that means that our vector, this is called a polarization vector, by the way. Our polarization vector, the components of the polarization vector is not, the components are not linearly independent. Since if we know what K naught is and K3 is, if we know K naught and K3, we can just deduce what E naught and E3 will be. So E naught will depend on E3, or you could rephrase it as E3 will depend on E naught, so they depend on each other. And these two vectors in the middle, we don't have any constraint on them. These can be anything we want to. We are at liberty to choose what E1 and E2 can be. But our outside entries will depend on each other. So we say that the components, well, 2 components of the polarization vector are linearly independent, but the upper and bottom components are linearly dependent. So technically speaking, we have only 2 linearly independent polarization states. Now here's where I start to quarrel with some of the modern conventions in quantum field theory. So you will hear people say a lot that the polarization vector has 3 linearly independent components, right? And the reason they say it's 3 instead of 2 is that you could, in principle, consider E1, E2, and E3 to be linearly independent, right? You can just say, oh, E1 can be whatever, E2 can be whatever, and E3 can be whatever. And then E naught will depend on E3. So we can choose the bottom entries to be whatever we want, and it's just that E naught will depend on what we chose for E3. So by saying that, we can conclude that it has only 3 linearly independent states instead of 2, right? But my problem with this argument is like it kind of goes both ways, we can just say that, oh no, E0, E1, and E2 are the linearly independent components. And then E3 depends on E0, right? It's really arbitrary. So really, it's not that E3 is independent and just like E0 depends on E3. It's really that they depend on each other. So I would say that there are only two linearly independent components, but most textbooks will say that there are three. It's modern convention that there are three, even though I think it's dumb. So we will just say that there are three linearly independent components. So again, it just means that physicists can just choose what we want for E1, E2, and E3, and then we can just deduce from E0 from that. Well, it technically goes both ways. So yeah, this means that our polarization vector for a mass gauge field will have three linearly independent components. So I actually looked a bit more into it, and I found that we were actually correct. So E rho has two independent components. So like it's not a thing. I misinterpreted something that I read. So no one is saying that E rho has three independent components. They're all saying that E rho has only two independent components. So we were actually right. So when I said that everyone else says it has three independent components, forget that I said that. They don't. So everyone else does agree that E rho has two independent components. And that's because we have the condition that E rho, or that E naught, K naught, equals E3 K3, right? So since E naught will depend on, will depend on E3, and E3 will depend on E naught, this means that it will have only two independent components. Now, I said linearly independent components, and that's technically incorrect. It should just be two independent components, because components are scalar quantities. So saying linearly independent won't really make any sense, since all scalars have linear dependence. So they're not linearly independent components. They are just two independent components. So E rho has two independent components, but it does have three linearly independent vectors. There's a big difference between the component and the vector. So remember that we can have a bunch of different polarization states. So like we can have, how do I say this? For example, like we can actually have we can have these polarization states. We can have the polarization state that is that's 0, 1, 0, 0. We can have a polarization state that is 0, 0, 1, 0. We can have an infinite number of polarization states. We can have, say, we can even have like 3, 0, 1, 0, 0 plus 2, 0, 0, 1, 0 as a polarization state. That's called a mixed polarization state, or a superposition of those states. So we can have a bunch of polarization vectors, right? So these are the actual vectors. However, the entries inside, those are the components. And the components, there's only going to be two linearly independent, there's only going to be two independent components. However, there are three linearly independent vectors. So what do I mean by vectors? Well, since we can have a bunch of polarization states, right? I'm trying to think of how to say this. So we can have a bunch of polarization vectors, right? And this comes from linear algebra. For all vector spaces have what's called a basis, and the basis is used to build larger vectors. And because of our condition that e rho is going to equal this, it implies that there are three linearly independent basis vectors for our polarization space. And these are the three listed here. And we can understand why there are three, because one of those polarization states is going to have two of its components being related, right? So normally we can have four linearly independent components, right? But because we're going to have this one, but because we're going to have like two of those always being related, instead we are only going to have three linearly independent components. So I hope that now makes sense. So these are the three components, so not components, these are the three vectors that we choose as our basis. And we can choose really anything as our basis. We can choose any three vectors as a basis, as long as it actually is a basis. But we choose these three vectors specifically because they are very convenient, or they are very convenient to work with. For example, the first vector here, well, these two vectors, they're actually, they are orthonormal vectors, meaning that the dot product between them, the dot product of E1 with itself is going to be equal to 1. Same thing with E2. However, the dot product of E1 with E2 is going to be 0. So, yeah, they are very convenient to work with since they are orthonormal. And if you want to visualize these vectors, this vector is going to be, this is a unit vector, right? It's a unit vector pointing in the x direction. So that's why it's usually called the x polarization vector. And this one's pointing in the y direction. So it's called the y units polarization vector. So you might wonder why we have this mu component here. And the reason why I put this mu component is to distinguish the different vectors from the different vector components. So we can have the E1, E2, and E3 and E0 components, right? But it's not like these are their own vector. These are all components of a larger vector. So the reason why I put this mu here is to distinguish the components from the different vectors that we can actually have. It's to make it be less ambiguous. For example, like E1 mu will contain the components of E0, E1, E2, and E3, right? And this mu just signifies that, hey, it's like its own vector. And then E2 mu can be like E0 prime, E1 prime, E2 prime, E3 prime, and stuff. So I put this mu so you guys don't confuse this as a single component. So it's really just for notational things. So what's next? Oh, and we can actually check that each of these vectors satisfies our condition. So let's actually check that right now. So remember that our condition is this over here, or can be written like this. And then E1 mu is going to be 0, 1, 0, 0. So our condition now just becomes E0, which is 0, equals E3, which is still 0, times K3 over K0, and 0 does indeed equal 0. So this does work as a vector. What about E2 mu? Well, E2 mu is just 0, 0, 1, 0. So it still satisfies our condition since E naught is 0. That equals E3, which is 0, times K3 over K naught. And 0 does indeed equal 0. So this does also work as one of our basis vectors. Now, what about this one over here? This one is a bit more strange. Like, you might ask, well, why can't we just use, like, say, 0, 0, 0, or sorry, 0, yeah, 0, 0, 0, 1 instead as a third basis vector? Or why can't we use, say, 1, 0, 0, 0? And the reason is that these don't satisfy the, like, our condition, our polarization condition. So let's just check that right now. So some hypothetical E3 would be 0, 0, 0, 1. And here is our condition. So E naught, that's just going to be 1. E3 here is going to be, sorry, E naught is 0. E3 is 1. Since recall, this is going to be E naught, E1, E2, and E3. So E3 is 1, and they have K3 over K naught. So K3 and K naught are obviously going to be, at least we are making it be non-zero. I don't know how I'm supposed to phrase this. Since remember that K is K naught, 0, 0, K3. Yeah, this should actually be, these should be upstairs indices, really. So K naught and K3, they're going to be non-zero, right? So 0 is going to equal some non-zero number, right? But 0 is not equal to something that is not 0, right? So that's a contradiction. So we can't have that as a polarization state. Same reason with this guy over here. It also violates that condition, and you guys can check that yourself. So let's just clean this up a tad bit. Let's clean this canvas. So let's actually check now that our third vector satisfies our condition. So our third vector is this guy over here. Oops. Is this guy. Yes, let's copy that. Paste that. And we can like just erase this over here. Yeah. So let's see if it satisfies it. So this is going to be E naught, here's E1, here's E2, and here's E3. So let's check this. So first of all, this means that K3 over M equals E3, which is K naught over M, times K3 divided by K naught. Is this true? Well, yes, it is true. K3 over M equals K3 over M. So this does actually work. Yay. So this does work as a third polarization vector. Now, you guys might be wondering, why do we have this pesky mass term here? And that's just for normalization. We can take the dot product of E3. Also, this is going to be called EL, by the way. By convention, we like to call this EL. So the dot product of EL with itself is going to be equal to K3 squared over M minus K naught squared over M squared. Remember that K naught is the square root of M squared plus K squared 3. This comes from E equals MC squared. And this is being squared. So this is going to be over m squared. And that's just going to be equal to k squared 3 over m squared minus m squared plus k squared 3 over m squared. This comes out to be minus m squared over m squared, which is just minus 1. So this is normalized by some -1 factor. So this is going to be equal to -1. All right. So we've shown that it is indeed normalized. Well, I guess you can say reverse normalized. I'm not really sure what you'd call normalization if the dot product is -1. All right, we're almost done here. Hang in there for the last few minutes. So some terminology here. The E1 and the E2 polarization vectors, these are called, I think, like transverse polarization vectors. And you guys can probably tell why. The reason is that they point in the x and the y direction respectively. So that's like translating, you know. And this third one is called a longitudinal polarization. Or yeah, polarization vector. It's called longitudinally polarized because it is longitudinally polarized. So that's just the names for them. And yeah, there are 3 independent polarizations for the solutions to the Proca equation. So when we consider things at rest, some interesting things start to happen. So we know that the Proca equation describes light that has mass. So since it has mass, it's not moving at the speed of light, which means that it can be at rest. Or we can choose a frame where it's at rest. And if it is at rest, or better said, if the field is at rest, meaning that k, the 3 momentum k vector, is going to be 0, that causes some non-trivial things to happen. So first of all, let's do some brief review. So k with a vector, that's just the 4 momentum vector that has components of k0, k1, k2, and k3. So this first component is just going to be the energy, or it's related to the energy. I already said this, but I just wanted to say this again. And these bottom 3 components, these are like the actual momentum of the particle. And if the bottom 3 entries are all 0, this means that the particle has 0 momentum, right? And since momentum equals mass times velocity, if the momentum is 0 and the mass is non-zero, that means that v has to be equal to 0. So this corresponds to the particle not moving. Now, since E equals m squared plus p squared, or E squared equals that, and there's no motion, this means that p goes to 0. So we get E squared equals m squared, or better said, k naught squared equals m squared. So since k naught squared equals m squared, we can just plug this into our equation that said that E rho k rho equals like 0, which means that E naught k naught is going to be equal to 0, right? And since since k naught squared equals m squared, this implies that k naught equals m. This corresponds to E equals m, by the way. So that means that we can just say that E naught times m equals 0. Which means that, well, yeah, it just means that the E component has to be, the E naught component has to be equal to 0. And that's our only condition here. E naught has to be 0. So if our particle is at rest, E naught just has to be 0, and we're good. So E is just E naught, E1, E2, and E3, right? Our only condition we have here is that E naught just has to be 0. So this is sort of like a loophole in our rule where we can have we still have 3, right? 3 or 2. But we have a loophole here where we can allow a third in E3 polarization state that's equal to all entries 0 but 1 at the bottom. Since as long as we have that 0 in the first entry, we're good. So that's a sort of loophole to allowing that third polarization state if the particle is at rest. Now we know that our solution, or one of our solutions, was A naught x mu equals E rho e to the minus I k mu x mu, right? I'm going to erase this part. And, sorry, ignore the sound in the background. This was one of our solutions. And we can make extra solutions. So the Proca equation, it's what is called a linear differential equation. And if we have two solutions, this is a principle from linear algebra. If we have two solutions to a linear differential equation, the superposition of those solutions is also a solution. And we can actually verify that A rho x mu of E rho e to the plus I k mu x mu is also a solution. This should actually be obvious if you realize that, hey, the Proca equation satisfies the Klein-Gordon equation, and plus I k mu x mu is also a solution. So you have these two solutions, right? And then a superposition of those solutions are also a solution, right? We can actually sum over k mu. So we can just take a sum over the k mu variable. For example, we can have like k mu equals, like, say, I don't know, 1 0 0 0, or k mu can be equal to 3 5 2 7. And of all these values of k mu, as long as it obeys E equals mc squared, right? So you can sum over k, and since k is continuous, this means that the sum becomes an integral. So the sum will turn into an integral. I actually talked about these exact steps in my second video on the Klein-Gordon equation. So if this doesn't make any sense, try watching that video. And since we can take a superposition with complex coefficients, that means that the coefficients that we use become functions over k. Whoever is there, go away. I'm recording a video.
I need to look for my pen.
No, they're not here. I'm recording a video right now. You're on YouTube, by the way. I don't have any of your clothes, actually. Anyways, yeah, that was my brother, guys. Sorry about that. I literally have no place I can be in this house without some crazy person opening my door and just annoying me. So, very sorry about that. Anyways, I should probably edit that out, but I really don't have... I do have the time, but maybe I might edit that out. If you don't edit that out, well then, okay. Anyways, our coefficients are functions over k in this case, and yeah. Also, our polarization states, we can have multiple polarization states. And since we have multiple polarization states, we can also sum over those polarization states. And recall that we actually have 3 of those polarization states. And the superposition over those polarization states will also be a valid polarization state. And yeah, we can just sum over those ones as well. And if we scale those by coefficients, we can just absorb that into our plane waves. And by just combining all these arguments, we essentially get the general formula for the Proca equation, which looks like this. This is the most general solution to the Proca equation. This actually looks like the solution to the Klein-Gordon equation, right? Here is the solution to the Klein-Gordon equation. And it looks very much alike. We actually use only real coefficients because reasons. And, well, the reason is that, like, spoiler alert, we want only real particles and no antiparticles. But we will understand that once we get to second quantization. So this is the solution to the Klein-Gordon equation. We can actually see that solution almost hidden, hidden in plain sight, in the solution to the Proca equation. What's different is that we also have these polarization vectors, and that accounts for our internal vector structure of the Proca equation. So that is the most general solution to the Proca equation. And now I'm going to jump off a window because my family is very annoying. They're super annoying, and I'm very mad right now since there are many interruptions in this video. I told my brother to not come into my room. He came anyways, so I'll be 18 like in 2 years, about like a year and like 5 months. So once I move out, no more distractions. All right, so thanks for watching. Also, if we have a sum to 3. So here, this R represents like each polarization vector. So like R equals naught can be like the E. Sorry, well, R should start at 1. It should start at 1. So the R equals 1, for example, that would be the E1 mu polarization vector, which looks like this, right? And it goes up to 3 since we have 3 linearly independent vectors. And then at 3, technically the R becomes an L since we have that. Since we had the like weird L vector. And yeah, if we were to graph this, it would look like something like this. So they're like plane waves, but they're formed by the vectors instead of scalars, which is pretty cool. Here's like A mu x. Yeah. And that is the solution to the Proca equation. This is the electromagnetic four vector potential. And that concludes our video. Thanks for watching. If you guys have any questions or comments, please leave them down below. And yeah, have an amazing day. Bye.